Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And this particular video here, we're going to be building on what we talked about on our previous video involving effusion and effusion rates, which leads us into various themes in terms of the relationships that are built not only in terms of the pressures but also the rate of effusion leading into the molecular mass of various compounds, and also how vapor pressure is incorporated into the formula, which we did on our previous video, where we explored this new equation where our pressure, vapor pressure, is inversely proportional to the molecular mass of that particular compound or molecule that is in that particular space, and also inversely proportional to the area of that particular hole that is created when you actually let particles to leave or escape at a specific time interval. So these are the things that we did on our previous video, and in this video we're going to build on this particular expression to be able to analyze a particular question which says this: the effusion cell has a circular hole with a diameter of 3.0 millimeters if the molecular mass of the solid in the cell is 300 grams per mole and its vapor pressure is around 0.224 pascals at this particular temperature. By how much will the mass of the solid decrease in a period of 24 hours, which is approximately a day? So let's dive into the solution to this particular problem, and the solution will enable us to first, how about we design a diagram that expresses this particular situation. And so in this particular diagram we have a specific effusion cell, and in this region we do have very hot solid that will be experiencing a form of a liquidation process. That means it is very hot, and once it's hot it releases various particles that exerts pressure around this cell. Therefore the vapor pressure is going to be considered in this particular system, and as a result of that we can result in a specific effect where we create a hole, or we puncture a hole where the hole is expressed as a knot, and this leads to a leak where we have particles escaping. Now the rate at which the particles escape, which is the rate of effusion, is equal to the vapor pressure in here. Reason is because as molecules leave, we have new molecules being replaced from the hot solid liquid region to the space. Therefore, based on this, we are going to be able to analyze various givens in this question and then create our solution steps. So the givens are as follows. We have first the diameter, which is represented as the, nope, we don't have the diameter. We have, yes, the diameter, and the diameter of the hole is represented as this particular number, which is 3.00 millimeters. And take note that since we're given the diameter, we need to get the area, because that is what we are focusing on. And so the area of the hole, since we're assuming that it is circular based on the question, we know that the area is pi r squared, and we know that r is related to the diameter. Therefore we can then lead our solution to a pi multiplied by 3.00 times 10 to the, take note that we need to convert our millimeters to meters. Therefore we have to the power of -3 meters. Take note that all this is divided by 2 because half of a diameter is the radius. Therefore this, take note, is all squared. Therefore we can then get our area to be equal to, for the whole, 7.07 times 10 to the -6 take note that it is in meters squared. Now, the next is looking at other variables that are given in the question, which includes the following. We have the molecular mass of the specific solid to be equal to 300 times 10 to the negative 3 kilograms per mole. Usually is meant to be in grams per mole based on the question, but in here we're changing to kilograms per mole because we want to obey the standard units. And then our next part is looking at the pressure, and the pressure here is around 0.224 pascals. Pascal is the standard unit, and temperature here is equal to 450 kelvins, which is also a standard unit. And we are also given the time interval by which the particles are living to result in the change in the mass. So the time interval in here, it is around 24 hours, and we know to convert from 24 hours to seconds. Seconds is a standard unit. We multiply by 60, and we also multiply by 60 because 60 in here minutes makes an hour, and this 60 here is 60 seconds make a minute. So as a result of that, we are able to get our answer in seconds to be equal to 84,400 seconds. And so we are able to get our givens in this particular question. And the next one is to look at what the question is asking for, which is the required. And based on the question, which is above, we can then assume that based on this, we have by how much will the mass of the solid decrease. Therefore, once you have this loss of particles here, we actually lead our particular system to a decrease in the mass, starting from the green barrier to this red barrier right here. And so the red barrier tells us the mass after versus the green barrier, where it tells us the mass before. So as a result of that, we have not only a relationship with our change in time, but this connects really well to the change in the mass. So based on the question, which is required, how much mass decreases as a result of this process, which means that we are going to find our change in the mass. And so this mass loss is the crucial point that we need to take into account or to investigate in this particular problem. Therefore, let's look at our analysis. Based on our analysis, we can actually assume various interesting terms in here, and the terms include the following. We know that the vapour is replaced one by the hot metal, and so once we take that into consideration, we can then assume that yes, the rate of effusion is constant in terms of where the pressure vapor is constant as well. And so this is despite the fact that despite the fact that effusion of the atoms is applied in here. And so as a result of that, we can then lead our solution in terms of the formulas that we're going to use to be based on our flux, which is a collision flux. And the collision flux, we know, since it's equal to the pressure multiplied by our Na, which is the number of particles, over square root of 2 pi. We know that this is the big M, the molar mass, multiplied by RRT, and this is also equal to relationship with the change in mass, where our change in mass is all divided by the area of the hole multiplied by the mass of that particular particle. And take note that it is for one atom, is also multiplied by our change in time, which is the time interval. Now take note that where we have our number of particles to be equal to the gas constant multiplied by our Boltzmann constant, and we know that the mass of one atom is equal to the molar mass divided by the number of particles. We are going to put this in equation 1, which is what we have right here. And take note, when I mean equation 1, we are using this particular segment of our equation. So therefore, where we see Na, we're going to, in this particular part, we're going to put our T over T, and then for our mass, we have mass at the bottom denominator, we are going to put M over Na. Therefore, we are eliminating the number of particles and also the mass of the particle, one atom specifically, because those are not given in the question. Therefore, we are then going to solve our equation and put it in terms of our desired variable. And so therefore, we have first our pressure to be multiplied by our R over K, and this is over, take note, we have square root of 2 pi, this is molecular mass, and our T, this is equal to our change in the mass, all divided by the area of the hole, and this is multiplied by mk over the R. So this is all then multiplied by our change in time. And so take note that a couple of things are going to be cancelling out. R will be cancelling out our other R on the other side here. We have our K cancelling out this K. And what else is actually happening here? That is all that is cancelling out. And as a result of that, we have our new expression in terms of pressure on the left side, and also in terms of square root mRT, and this here is equal to our change in the mass all over our area of the hole. Take note that we have our m that is left, which is in molecular mass, times the change in time. And so here is where we're going to solve for our change in mass, which is an indication of our, take note, the lost mass or the lost mass. Therefore, we are going to have a new expression for our mass change to be equal to, take note, we have our pressure multiplied by the area of the hole multiplied by the molar mass multiplied by our change in time all over our square root of 2 pi m, which is the molar mass multiplied by R and T. And also take note that this, when you rearrange this particular expression, because we have a couple of common terms in here, we have our molar masses at the numerator and denominator, and in here we can now re-express this here also in terms of an overall square root, where by considering this we can derive this new expression, which is all square root of our m all divided by 2 pi RT, and this is multiplied, take note, by the area of the hole multiplied by our pressure and our change in time. So this is our golden formula that will be used mainly in solving this particular problem right here. And so putting our givens in this particular expression, we are going to get our new expressions in terms of the solution. And so therefore our solution is going to be, or solving is going to be, putting our givens, and we have our change in m to be equal to our square root. This is going to be a big square root of 300. That is our molar mass in terms of grams per mole, kilograms per mole all divided by 2 square root of 8.314. Take note that this is in joules per mole per Kelvin, and this is multiplied by our temperature, which is 450 kelvins. And take note that we have our area of the hole to be 7.07 times 10 to the negative 6, and we have our next one, which is our pressure, to be equal to 0.224 pascals. And finally here we have our time to be in seconds, 886,400 seconds. And so whilst we have this taken care of, let me just erase this because it's not really required, because we're going to get our final expression. Yes, that is good. And so as a result of that, we have our change in the mass to be 2 segments that will be multiplied. One is our square root of the inside, which is 1.276 times 10 to the negative 5, and on the other side we have 0.13680. And so therefore, once we have this, our change in mass based on that square root is equal to 3.572 times 10 to the negative 3, and this is multiplied by the same constant. And so therefore our mass, take note here that the mass is measured in kilograms here, and also in kilograms, and also here in kilograms. I'll challenge you to play around with the derived units and be able to determine the units, which must be in kilograms. That is the challenge I'm going to give you all. And so our change in mass in this particular case is a loss of around 4.888 times 10 to the negative 4 grams of our specific solid when you create a hole of that size, which is shown right here, and you have this particular hot solid at that particular temperature and at that particular pressure. And so that is about it for this particular video. Hope you're able to understand this analysis based on this expression, and how, you know, at that particular temperature, 24 hours, hour time, which is 24 hours, that is a lot of mass that is being lost during that particular process. And it's quite interesting to see how this plays out in various systems, mainly dealing with solids. And so that's about it for the particular video. Hope you found this really informative. Hit a comment down below, let me hear your thought about this. By that way, I can talk to you all soon. Stay smart as always, and believe in yourselves.